The third way we can solve systems of linear equations involves a matrix. And a matrix is just a rectangular array of numbers. It's just a different way of writing linear equations. And notice on the screen I've got a system of linear equations, only this time I've got 3 equations in my system. And I can write this as a matrix by leaving off the variables and just writing in the numbers. Notice that each number corresponds to the numbers in the matrix. We've got the coefficients 2, 4, and 6, and that's equal to 22. And that goes on the right-hand side of the vertical line. And same thing goes with the remaining linear equations, 3, 8, and 5 are the coefficients, and that's equal to 27. And for the third equation, my coefficients, negative 1, 1, and 2, and that's equal to 2. And just the set of numbers to the left of this vertical line is called the coefficient matrix, and the numbers to the right are the solutions. And there are some important rules to be able to follow in order to solve a matrix, which we call a solved matrix to be in row-reduced form. Number one, each row consisting entirely of zeros must lie below all the rows having non-zero entries. And notice in here, this is an incorrect way to express this matrix. This is not in row-reduced form. To write this in row-reduced form, the row with all zeros must be at the bottom. That would be the correct way of writing that. Number two, the first non-zero entry in each row must be 2. And this is called a leading 1. So in this matrix here, the first row is fine. The first non-zero entry is 1, but in the second row, the first non-zero entry is 2 and not 1. So that's why that is not in row-reduced form. Number 3, the leading 1 in a lower row must lie to the right of the leading 1 in an upper row. In my example here, this is not correct because the lower row, the leading 1 in the lower row, lies to the left of the leading 1 in the upper row. And to fix that, we can just switch those 2 rows. And then number 4, if a column in the coefficient matrix contains a leading 1, then the other entries in that column must be zeros. So, for example, here's my 1, my leading 1 in the first row. So this means that every other entry in this column goes up and down, must be 0. And I've got a 0 here, a 0 there. In the second column, my leading 1 is in my second row with zeros in the other entries in the column. And my leading 1 in the third column is in the third row, and I have zeros in all of the other entries. So this would be an example of a matrix in row-reduced form. And this matrix is actually the solution of the above matrix, and we're going to learn how to work through the steps of getting from this top matrix down to the bottom matrix. But this bottom matrix can be interpreted back into the system of equations. And keep in mind that the first column represents all your x values. Your second column are your y values. And your third column are your z values. And we've got zeros in 2 of our variables and a 1 in the other variable. So that means that the first row tells us that x equals 3. The second row tells us that y equals 1. And the third row tells us that z equals 2. And so this would be our solution of our system of linear equations.